Good afternoon. My name is Ashok Gadgil. I'm the Division Director for Environmental Energy Technologies Division. And it's my great pleasure to introduce Professor Linda Nazar. She's a professor of chemistry, physics, and electrical engineering at the University of Waterloo in Ontario, Canada. And as the three-disciplinary overlap indicates, she has actually fingers in many areas, all of them focusing on materials for energy storage and conversion with research that spans lithium-ion, sodium-ion batteries, lithium-sulfur batteries, and lithium-air batteries, and fuel cell catalysts. Professor Nazar has a number of awards and honors and holds a senior Canada research chair in solid-state energy materials. She was in 2009 received the Electrochemistry Society's Battery Research Award. Last year she was the Moore Distinguished Scholar at Caltech, and this year she received two awards, the International Battery Association Award and the IUPAC Distinguished Women in Chemistry and Chemical Engineering Award. And she also has been elected to Fellow of the Royal Society of Canada. So without further ado, Professor Nazar.
I think I'm wired up. Well, thank you very much for that kind introduction. That was very, very nice. It is really my pleasure to be here, and I thank you for the invitation to come and visit. And I'm sorry about not being able to visit in January. I'm somewhat better now. And so today I'm going to talk about energy storage. The part about the climate change is really just to woo people into the talk. I'm not really a climatologist, and I'm not going to be talking too much about it. This pretty picture is not of Waterloo, I'm sorry to say, it's of Toronto, but it's our airport, which is about 45 minutes from my house if I drive quickly. And at Waterloo, we have an Institute for Nanotechnology. We also have Waterloo Institute for Sustainable Energy and an Institute for Climate Considerations, and also quantum computing and all sorts of other things. And I am predominantly affiliated with these two institutions, so we don't have a material science department, which kind of makes me delocalize somewhat. So I will address a few issues of climate change, but as I said, very, very briefly. And just to bring up a couple of points, this is in May. I watch the BBC News on a regular basis and read their website. And so on the 30th of May, they pointed out that the global carbon emissions have reached a record, according to the IEA. And this is, of course, another wake-up call, pointing out that we're not really going to reach the level of emissions that we should not be reaching until 2020 if this so-called 2C target is going to be attained. That is the target for the reduction of emissions. And whatever one can say about global climate disruption, certainly carbon emissions are a part of it, I think that most of us would agree. So it turns out that the day just before that, on the 29th of May, the BBC happened to report that the Saudi prince bin Talal said that he wants oil prices to drop so that the United States and Europe don't accelerate efforts to wean themselves off the country's supply. And he clearly actually said this. I saw the interview. We don't want the West to go find alternatives, because the higher the price of oil goes, the more they have incentive to go do that. So, of course, the economy seems to be fixing the problem right now because the price of oil is down, but that's, of course, not what we really want to have happen. And in Canada, we particularly see the effects of this with the reduction in the sea ice, which is, this data is from the Copenhagen Climate Science Report in 2009, and this has only become more significant with the diminution of the sea ice. And of course, for Canada, this means that now a lot of water can be opened up and all kinds of economic advantages accrue, but of course there's an enormous amount of economic disadvantages that will accrue from this. So I think it would be safe to say that this is a threat to humanity in the 21st century if it continues unabated, and it is certainly a scientific challenge of our time. So energy storage is certainly not going to fix the problem. There's many solutions or many ways that one can approach this. And that includes investing in catalytic chemistry, more energy efficient reactions and processes, CO2 sequestration, for example, photovoltaics, most certainly, perhaps hydrogen generation, and energy storage is on the bottom of the screen and it's cut off. I don't know if it's possible to fix that, the people that are running the video, but anyway, there's energy storage at the bottom. So, as I said, energy storage is only part of it. It's really what we're looking at is trying to manage energy demand through energy storage. And this is obvious, I think, to many people in the audience. Solar, wind, and wave are intermittent supplies that have to be coupled to energy storage devices in order to effectively make them dispatchable sources of power. And of course, there's also the electrification of transport. And this is very much a commercial concern at the moment, and to a certain extent a government concern. And this can lead, of course, to a reduction in CO2 emissions and the conservation of oil. So energy storage is critical for both of these. It would be safe to say that lithium-ion batteries are probably not going to be economically viable for this purpose, although the jury is still out on that at the moment. There's probably other forms of energy storage that are necessary, and certainly lithium-ion technology or lithium technology is going to be an important point of the electrification of transport. So I stole this slide from the DOE, and this is what in electrochemistry we call a Ragone plot, which is just a plot of energy versus power. And so this axis, for the non-electrochemists in the audience, basically refers to the range, and this axis effectively refers to the acceleration of one's vehicle. And so this is good old lead acid, and this is nickel metal hydride that is still driving the Toyota Priuses, and this is a lithium-ion cell as it currently stands today. So if we take a look at where we need to go in these systems, PHEVs are, for at least short-range transport in the vicinity of 20 to 40 miles, pretty much adequate if that's all that you want to go. The problem is that, of course, people don't want to drive for just that distance. There are various targets that have been suggested, ranging from 100 miles to 500 miles, but perhaps 150 is appropriate. And certainly none of the batteries really match the EV goal at present. So, not surprising, we need to find better energy storage systems. So it turns out that electrochemists are, first of all, in short supply in the US, perhaps not everywhere in the world. They are also in short supply in Canada. But it's a well-worn technique. Some people think that Volta was responsible, but it appears that, in fact, it was developed in, well, a long time ago. So these devices, which are quaintly called the Baghdad battery, have been unearthed. They exist in the Baghdad Museum, and they are excavated from Sumerian sites dating back to 2500 BCE. And it's effectively just a good old electrochemical couple between, there's an iron rod that sits in the center, copper sheet on the outside, and it is thought that the electrolyte was something like citric acid or vinegar or other type acidic solutions. And when these things are coupled up, they actually produce a current. A woman who's at the Naval Research Labs, Deborah Rawlinson, and I we edited rather, an MRS bulletin edition, which has just come out. And Deborah actually has built these in her lab just for the sheer fun of it to prove that they work. And so you can see a picture of one of them, not from the Baghdad, not the museum, but the actual battery. So it would appear that the Parthians inherited their batteries from one of the earliest known civilization. And of course, this is just the general concept of energy from chemicals, using the well-known Gibbs equation. So then if we consider what electrochemistry can do for us, well, there's electroplating, which is possibly what they did with the ancient Sumerians. So this is just chemicals to other chemicals through electrochemistry. There's also chemical energy to electrical energy in work, which is the normal discharge of a battery. For example, the functioning of your primary cell that you use in all the time. And then finally, there is the real frontier, which is converting the electrical energy to chemical energy, which is the battery recharging. And this is of course, the storage problem that challenges PHEVs and the renewable energy technology. So if we go back, moving on from the Sumerians, a little bit forward in time to the lead-acid battery, developed by Planté in 1859, this is a pretty simple reaction. And the point here is that this reaction works in the bulk, and it's actually pretty amazing that it works at all. So there's two electrodes, And effectively, it's the conversion of lead to lead sulfate or lead oxide to lead sulfate, which drives the EMF difference between them, which drives the reaction. And of course, sulfuric acid is an electrolyte. And that has a pretty poor gravimetric energy density, and some of these numbers will come up again, so perhaps keep them in mind. So this is 30 watt-hours per kilogram with a volumetric energy density of 60 watt-hours per liter. And it has problems of durability and self-discharge, but they still work pretty well. And in general, one, I think, can say that the success really depends on the kinetics of the electrolyte and the electrode processes. And so the persistence of the technology is really around, despite this unfavorable mass, because of that kinetic factor. Unless you think that everything is known about lead-acid batteries and that they're really boring, my other favorite magazine, The Economist, and there's an article here on Einstein and car batteries. So I won't tell you all about the article because it's rather long, but the point is that apparently the batteries in your car actually have something to do with Einstein, and there's even a Fez Roulette article just out this year all about that. So there's always more under the sun than we think. Okay, back to a step next in history. So from 1859, we now move to sort of the 1980s, and this technology was being developed at a lot of places around the world, at Exxon Corporate Research, where I started my postdoc, but even prior to that at the University of British Columbia, where I did my undergrad. And this physicist, Professor Rudy Herring, he didn't really patent the first rechargeable lithium battery, but they were the first to commercialize it. So this slide is slightly in error, because it was the first, as I said, successful system. And it was based on a reversible reaction in a cell, which involves a nice cheap material, molybdenum sulfide, and one can then use this as the positive electrode. It will react with lithium, and when it is delithiated, it forms a highly conductive form of the molybdenum sulfide. So the starting material is actually a semiconductor, and this reaction changes the phase and turns it into a great conductor by processes that are understood by solid-state chemistry. And it was this then that really started this company. They used metallic lithium as a negative electrode because they didn't know any better in 1979, and ultimately the technology failed due to problems with dendritic growth of that metallic lithium negative electrode. Now, back in those days, they were using electrolytes that we've gone far beyond that. Separators weren't developed, all sorts of things weren't developed. But it did sort of jumpstart a lot of interest in the area. And so today we have lithium-ion cells, and this little cartoon shows how they work. So in short, while you watch this thing cycle around, I will explain that no longer, at least in a commercial lithium-ion cell, do we have carbon. So this is the negative electrode, which is a carbonaceous electrode, which replaces the lithium, and a positive electrode, which intercalates or incorporates lithium at a high redox potential versus the negative electrode. So during the process of discharge, the lithium ions enter the positive electrode, and during the process of charge, they enter the negative electrode. And so the lithium ions shuttle back and forth between these two host materials. Now this cartoon is carefully designed such that it marries this process. So this is the process on discharge, and the voltage goes down in the cell, and then we recharge the battery, we shove the lithium back into the carbon, and it comes back up again. And you can see that the energy difference between those two electrodes actually changes as a consequence of the fact that the Fermi energy of this positive electrode is changing. So we call this a double intercalation cell. Sometimes it's called, the Japanese used to call it a shuttlecock cell. But the point is that it works very well, and it's also limited by both of the capacity of the positive and negative electrode to accept the electrons, because in this process, the electrons are transmitted through this external circuit. So the positive ions effectively are just there in order to account for charge balance. That's all they're really doing. Now, they do, however, have to be hosted in either the positive or negative electrode. So the limitations in the system are due to the fact that either mass, either one of the electrodes can't accommodate that much lithium, or electronics, they can't accommodate that much electrons without undergoing a phase change. So I'll be talking later about systems that do not operate on this principle, that get around some of these issues. So in the last, since 1991, we've gone from small scale to needs of large scale systems, and we've also gone from micro to nano systems. So back here in 1991, lithium cobalt oxide was the positive electrode in that cell that I just described. And we've gone through some developments. I'll tell you a little about lithium iron phosphate today. And here we are, well, this is a little out of date, but effectively we're still here in 2010 with some other oxide materials, and lithium iron phosphate has now been implemented. For those of you who are, again, not electrochemists, we have a figure of merit, which is a gravimetric capacity, which is calculated quite easily by the number of electrons transferred in the reaction, Faraday's constant, and the molecular weight. So obviously, for a high-capacity cell, one wants a large number of electrons to be carried to a large amount of electrons in the reaction, and one wants a low molecular weight. And limitations to intercalation systems then rely on this value n, because it's very hard to transmit a lot of electrons in the reaction, whereas the integration reactions, n is somewhat less limited. So the intercalation systems worked really well for driving small portable devices and laptops and things of the sort, but these days we're trying to find batteries, for example, to fit, this is a picture of the Tesla, because it comes from California, and also we're trying to get to small-scale systems for medical applications. This just shows an implantable battery. So along with that, we have, as I said, gone from micron to nanoscale systems in order to achieve some of these requirements of these demands. And this is just a cartoon that illustrates the advantage of going from a bulk material where you have a lot of mass transport limitations to a nano-sized material where, of course, the path length for transport is far diminished. And one can also then imagine going to nanostructured materials where they convey all of the benefits of nanoparticles, but in a system that is somewhat larger and spans microns. So in this case, the materials will have a high tap density, which refers to the actual density that you can get in the electrode, but there can be low utilization due to these diffusion limits because of mass transport. Here we have enhanced kinetics. These materials can be hard to fabricate. In this case, as I said, they convey the advantages of a nano size, whereas they're much easier to handle. So just to remind you of those limitations of mass transport, the time in any system for intercalation can be described as the diffusion square of the diffusion distance divided by the diffusion coefficient. So you either minimize the diffusion coefficient or you change your diffusion distance. Pretty simple. So the other then consequence of moving to nanomaterials, nanostructured or nanoparticulate systems, is the fact that the surface reactivity is always a concern in any electrode, in any battery. So at the positive side of the cell, there is electrolyte instability to oxidation, and the negative side, there is electrolyte instability to reduction. So the smaller these particles get, the more the surface area obviously is increased, and the more destructive these side reactions in the surface can be. So we always have to work within the thermodynamic range of the electrolyte, and that's what really limits the energy of the cell. So we have our gravimetric capacity that I just described, which is a combination of that at the positive and the negative electrode, and then the energy of the cell gives us, the voltage of the cell gives us the total energy. So the capacity times the voltage is equivalent to the energy density. So the more we can separate these two, the higher the energy we can get, but we're ultimately limited by the electrolyte itself. So I'll be talking about positive electrode materials in today's lecture. Exclusively, although there's certainly a lot of work to be done on the negative electrodes. And in this case, there is particularly a problem with, as I said, reactivity with the electrolyte with respect to oxidation. So surface coatings and other processes have to be implemented. So the first portion of the talk will basically be discussing polyanion materials. And the first of these is lithium iron phosphate. So its structure is shown here. It is, I often like to say that it is along the lines of Helen of Troy, who launched 1,000 ships. This structure has launched 1,000 papers, probably 1,500 at this point, if not more. And these are sometimes called generation 2 batteries, although they're almost generation 1 at this point, because they are being implemented as we speak. And here is a plant which is using these devices for energy storage in the 100 megawatt hour range. This is a company down in Texas. So this material called triflite, lithium iron phosphate, is cheap, low cost. It's resource unlimited. It has high safety. It has all of the right characteristics except for poor conductivity. And it was reported by Goodenough in 1997. And it has been, as I said, the subject of much work since. So it has octahedra of iron oxide with tetrahedrophosphates, lithium ions running down these tunnels. And the reaction can be described as this. All of the lithium effectively can be removed from the material at a potential of about 3.5 volts. And it gives rise to a capacity, a theoretical capacity of 170, which can effectively be realized almost realized in practice. Our work on this started in 2000. 2001 is when we actually published this. And Michel Armand at the time was a step ahead of us. They were looking at carbon nanopainting, as they called it. This is our work where we took carbon precursors, milled them up with the lithium iron phosphate precursors, milled them up with carbon, and effectively used these as a kind of a shrink wrap to constrain the size of the particles. So we ended up with composite materials that were about 10 to 15% carbon, in which we constrained the growth of the lithium iron phosphate. And then moving along to 2004, we considered a different sort of process, which is effectively to use carbothermal reduction to convert the carbon to a combination of FeP and a metallic iron phosphocarbon glass. This is a metallic glass which has a conductivity similar to that of iron phosphide. So this is a cartoon of an actual TEM image where we did careful analysis of the grain boundaries and learned this is the iron phosphate particle itself shown in yellow, and the grain boundaries shown in gray and blue contain this mixture of substances. And it's kind of complicated to go through in this talk, so I refer you to our paper. But effectively, the process relied on the fact that if you take this iron phosphate, which is slightly substoichiometric in lithium, and you heat treat it gently, you phase separate out an iron pyrophosphate, and that material is quite subject to further reduction to FeP. So on the old Ellingham, on the carbothermal reduction diagram, this is more prone to reduction than is this. So it reduces and this does not, and it basically casts out this material on the surface of the material, on the iron phosphate. And more recently, so this led to what we consider to be a new area of surface transport of electrons. And more recently, Gerrit Cedar has used a rather similar technique to cast out a lithium ion conductor on the surface, which is lithium pyrophosphate. So this is just the same schematic. I just used the same cartoon showing now the growth of Li4P2O7 on the surface of these particles. And this is reputed to be a fast ion, or at least a fairly good ion conductive material. So instead of forcing out the formation of the FeP2O7, he forced out the formation of the lithium iron by simply going substoichiometric iron. So the same sort of idea. And the other concept here is that this glassy coating of this iron pyrophosphate rather, seems to control growth. So they were able to produce defect-free materials with this ion conductive coating. This material has enabled very rapid discharge rates with good capacity, and is sort of a bit controversial, so I won't get into it. So where do we go from there? Well, we have new positive electrode materials. This just shows a whole lot of them, most of which are theoretical. So these are the dark little splotches here. These are the ones that we already know about. And the take-home message from this slide is that we can, in principle, get to energies of 1,000 watt-hours per kilogram by accessing some of these new materials. And accessing those new materials is rather difficult. So we have to rely on techniques that are not perhaps common to the solid-state chemist, ones in which we deviate from these classic ceramic methods and move down the scheme, although the area shows going up, into these other sorts of processes where we carefully control the chemistry so that we can access metastable materials, ones that would literally decompose at the higher temperatures, and also possibly access nanodimension materials, because ultimately high temperatures lead to large aggregation and large crystallites. So the ones that we know, the ones that we're particularly familiar with, are always the ones that Mother Nature makes, thermodynamically stable ones of bulk dimensions. Now, Gerrit Cedar has calculated well over 1,000 new materials, and so the hunt is on, and the question is how to actually get them. So as I said, the discovery of our materials is limited by our toolbox. So this is not a picture of a politician in Congress getting really upset with the way things are going, but this is a picture of a little hydrothermal worm. that apparently form in hydrothermal vents in the ocean. And we often wonder if we're missing these in our hydrothermal reactors, because the control of the chemistry in these hydrothermal bombs is really very much a kind of an art, and there's magic involved, and you throw things in and sometimes it happens and sometimes it doesn't. So as I said, maybe these little guys are necessary. But if you're lucky, you can control the chemistry. So this just shows an example of the synthesis of a new class of materials. These are lithium fluorosulfates. And this material, you can easily get 90% of the theoretical capacity at 3.6 volts, a little higher than the olivine I just mentioned. This requires virtually no fussy, complicated carbon coating, and it's because it has a different structure, which is called a taborite, which has three-dimensional ion diffusion rather than one-dimensional, such as the olivine. And in this particular case, we formed the material using just a glycol as our solvothermal reaction medium. And the reaction is probably easier seen here, and it is what we call a topotactic reaction. So we just take iron sulfate, and this is the heptahydrate. We convert it to a porous material by blowing off some of the water, and then this material can be seen as an HOH. So the H is exchanged for lithium, and the OH is exchanged for fluorine, and we end up with LiFeSO4F. And that little diagram is shown here. So this produces a slightly porous material that allows really good electrolyte access, which allows us to achieve fairly good energy densities at reasonable rate capabilities for the material. We've also done modeling studies, which are reported in this chemistry materials paper, together with Saiful Islam at Bath, and we've learned that the activation energy for ion transport is about half of that of the olivine. So not only does it have three-dimensional transport, it also has a much lower activation energy for energy hopping. And the point is that you can't make this material under normal solid-state circumstances. It decomposes before the kinetics will actually allow it to form. So another material that falls in the lines of this is a sodium-ion material. I'll just briefly mention. Sodium-ion cells are thought of as being a possibility for coupling to renewable energy. They're not going to be in automobiles because they don't have the gravimetric capacity nor the volumetric. But the fact is that sodium is abundant, it's less costly than lithium, and the demand for lithium is certainly going to rise as auto manufacturers, we hope, start to incorporate these in hybrid and electric cars. So there is certainly a reason to look at sodium-ion materials, whether or not you think the reserves are limited. They're all in the high-Andean plains. So we developed a material which is, again, looks a little similar to that lithium iron phosphate. This is a completely different structure. The material forms as this sodium compound. The sodium can be exchanged readily for lithium, so you can also use it for lithium purposes. But the point is that there's two sodium ions in the structure, the pink and the green, so to speak. And on oxidation, just as in the case of lithium iron phosphate, you pull out one of those ions, and so it turns out that the pink ones disappear, and the green ones remain in place, and they effectively hold the structure together, and they stabilize it, they pillar it. And so that allows you to get away with a really low volume change of only 3.7% between the reduced and the oxidized form. And if you contrast this with lithium iron phosphate, the olivine, that's about 6.7%. So it has half of that volume change, which allows it to cycle much better. We call this a low strain material, and we reported this in 2007. This material also is metastable. It falls apart at less than 650, so we have to make it either by hydrothermal or solvothermal processes, because solid-state reactions, despite what the patent bivalent says, don't get you there, because it can't be made at 700 under ceramic conditions. So we were hoping that this would be a new family of sodium-ion conductors. It turns out that getting sodium-ion conductors to work well is very difficult, because sodium is just a little larger than lithium, and so in most cases the volume expansion on taking out the sodium, or vice versa, putting it in, is enough to cause enough strain in the material to result in really poor kinetics. So we were kind of lucky with this material because of this process of the so-called pillaring, and we're hoping to find other materials that behave similarly. So if I was to summarize at this point, I would say that the way in the future is to go from nanocrystallites, perhaps to nanostructures, which is what I'll be talking about in the second half, to interface organic, polymer, and inorganic material science, which is difficult for any one lab to do, because typically one tends to know one thing and often not a lot of others, and this is to define materials with tailored properties. To control and design grain boundaries at the interparticle and the interelectrode and interbattery level, which should have a big star beside it because it's incredibly important. And then finally, to turn back to the electrochemical reactivity of bulk solids, like I was discussing with the old lead-acid battery. So I sometimes refer to this as research, and that's where you go back and you sort of did what you did before, only you do it with a different set of eyes. That was actually from Gary McVicker, who was a colleague of mine at Exxon. He was the one who invented the term. So if we want to then think about going beyond the limits of intercalation chemistry to higher energy cells, where do we have to, what is beyond there? So this is the NMC material that this is nickel manganese cobalt oxide, one of those layered oxides I described. This is this is all gravimetric energy density. This is the same material coupled to a silicon negative electrode. This is the spinel, which is used in the Chevy Volt. This is lithium iron phosphate, which has actually made its way into the BYD car. And you can see that there is, respectable but not high enough gravimetric energy densities for these materials. If you look at volumetric energy density, now this material is looking rather good. But then there's these other gleams in folks' eyes, lithium-sulfur and lithium-air, which obviously offer, even from a volumetric perspective, much higher energy density values. And so we've effectively, I think, gone from way down here somewhere in the floor, which is the development of the Sony battery, through careful engineering to get us to these materials, which have now been expanded with a range of new materials formed by a series of complicated reactions, to now, as I said, what we call beyond intercalation. So that's what I'll be describing next. So this is just a comparison of batteries and fuel cells that kind of contrast the sulfur, the lithium-air, and the old fuel cell itself. So I'm going to start from the right and move this way. In a fuel cell, oxygen and fuel both off board, and the product is eliminated, good old water. So that's a great cell, except we know that there's all sorts of problems with it. So the lithium-air cell has oxygen as not on board, but the lithium is on board, and the product is also stored on board, which is ostensibly Li2O2. And the sulfur battery is rather like a typical battery, but it has something in common with this, which is that the sulfur is also stored in a carbon cathode, as the peroxide is stored in a carbon cathode here. And again, it has metallic lithium, at least at this point, as the negative electrode. And so I'll be describing these two cells, nothing about fuel cells today. So if we compare the reaction chemistry for these two systems, they're actually rather similar. This just shows the voltage profile for the lithium-sulfur cell and the reactions that occur, and this shows the reactions for the lithium-air cell. So in both cases, we have elemental either oxygen or sulfur starting off the process. We reduce the material to either form ultimately this soluble polysulfide, or in this case, this highly unstable reactive intermediate lithium superoxide. In the case of the sulfur cell, all of the polysulfides, there's a cascade or a sequence of them here, form a series of, they're a soluble species, and at this point, this system becomes insoluble as you move through this part of the regime. And in the case, again, comparing things, finally at Li2S2, we have an insoluble product, as we do in the case of the peroxide. So the oxygen mechanism has been elucidated by Abraham at Boston. So in both cases, the question then is how to actually make this cell reversible, because especially in the case of lithium-air, the primary cells have been known for a while. In the case of the sulfur, the reversibility is actually pretty easy. In the case of the oxygen cell, it's particularly difficult. And there are different problems with each cell, which have prevented either one of them being commercially implemented. In the case of the sulfur, it is the soluble polysulfides that are the problem. In the case of the lithium-air cell, it is the reactivity of the superoxide and the insolubility of the peroxide that are effectively some of the problems. So we have been addressing this problem through the design of porous carbons, because those are required for the host and they're required to electronically wire the system. So this just shows a typical sort of cooperative assembly using surfactants to assemble a silica, which is then converted to a carbon. This is well established by many others in the field, including Galen Stuckey at Santa Barbara and Ryung Ryu in Korea. So If you control nucleation of these systems well, you can end up with nano versions of these mesoporous materials. You can in situ carbonize the surfactant rather than having to extract it and stuff in carbon afterwards to obtain relatively highly ordered materials. This is a catalytic carbonization process. And we've also used things such as metal thiocyanine to produce fairly graphitic versions of these materials, where you can see the graphitic peak in the X-ray diffraction pattern, compared that of using sucrose, for example, for stuffing. So these are just some of our initial attempts. We've gone a long way in looking at different sorts of carbons, which has led us into interesting avenues. So I'll briefly describe these then for the sulfur cell. So I already explained that you start off with elemental sulfur in this cell, and push the wrong button. So this is just described by this block of sulfur. And if we then start reducing, we go through our cascade of polysulfides, including S8 2- and the S4 2- species. And in principle, these are then contained within this carbon host, which is not shown in the diagram. If you continue to reduce, you end up, rather than sometimes reduction, enforcing what's called a shuttle mechanism. Because of the solubility of these sulfides, they diffuse out into the electrolyte. And they will engage in a sequence of redox reactions where the more reduced species is sequentially reduced and oxidized within the electrolyte. So effectively, this transports over to the negative electrode and back to the positive electrode. And this little shuttle mechanism operates within the electrolyte. It actually serves as a safety mechanism, but it also reduces the efficiency of the cell dramatically. So this is to be at all cases, under all situations, avoided, or it is to be avoided at all costs. So if you can avoid it at all costs, that means containing these soluble polysulfides in the positive electrode, and that then allows one to get down to deeper capacities. There's a lot of reports in the literature, should anybody be reviewing lithium-sulfur cells, that present capacities about 420 or 500, and the fact is that cells that usually cycle about 500 milliamp hours per gram usually just work in this soluble polysulfide regime. So in order to get down to the deeper capacities where lithium sulfide is formed in the positive electrode, one, as I said, has to contain these. And at that point then, just at the bottom.
Just to understand this cell a little better.
Sure.
My impression is that both electrodes have carbon in them.
The lithium does not have carbon. This is carbon-free, so the lithium, the sulfur and the products are contained in the carbon host at the positive side.
But metallic lithium is not safe to have, right?
In the long run, so that's a big question. Perhaps we can save that for the question period. Currently, the cells that we are exploring have metallic lithium as a negative electrode. Now, in 1979, it was not considered safe. We've come a long way since then. We didn't even have laptops in '79. So ways to protect the negative electrode, which are on the next slide, and a variety of other things can possibly get us there, but really the aim is to go to different negative electrodes such as silicon. Okay, so that's a short answer to your question. Yeah, but carbon just here. So this rather high capacity of 1675 results from the fact that we don't have an intercalation chemistry reaction, we just have a simple reaction of lithium plus sulfur to give Li2S. So I call, as I said, this an integration process. So the good thing about sulfur is that it's really abundant. If you have to go to Jupiter, there's tons of it there. This is the volcanic moon Io, which is absolutely covered, but it's only 150 tons on Earth, so we don't have to go to Jupiter anytime soon. And it's resource unlimited, even more so than LiFePO4. It's all over the place, petroleum, tar sands, all over the place. The resources between Canada and the US account for 2/5 of the world's total, so we don't have a problem there. This is from the US government database. So there's two approaches to sulfur batteries, and one of them is what I call, or what most people call, a catholyte cell. So that's where you just operate in that limited regime of the soluble polysulfides, typically speaking. So these ultimately would deposit on the metallic lithium negative electrode and cause all sorts of problems in soluble products. So such cells have to have a protective coating, which is an ion conductive glass. So that insulates those polysulfides from reduction, and therefore they do not reduce to form the insoluble precipitates, and the cell can carry on. So these are absolutely required. These were commercialized by Scion Power, working together with PolyPlus. And these cells have some advantages. They have high power because they're effectively a liquid electrolyte system. The product is stored in the electrolyte, but they have rather poor volumetric capacity, and that includes, typical values are 100 to 150 watt-hours per liter. Now, in the case of the cells that we are examining or we're trying to develop, we call these contained cathode systems. So we try to constrain the polysulfides to our carbon host. This gives rise to much higher volumetric capacities. I'll show you one for just our cathode, around 2,000 watt-hours per liter, so substantially higher. They do have somewhat lower power characteristics as a result of this. So I'll just point out that all of our studies are conducted with an unprotected metallic lithium negative electrode, which we consider to be the worst case scenario. And once one starts to do fancy things with passivating that negative electrode, it gets a lot better. But we're trying to really see what our positive electrodes can do. So we just, as I said, leave that unprotected. So for those of you who are not familiar with this, this is work we published in 2009, which is what we called proof of concept. So we organized that carbon, those little micron-sized arrays I showed you about 3 slides previous. We organized these. They have carbon fibers between them that effectively span organized space, which comprises pores of about 3 to 4 nanometers. So this is a very easy, fairly easily made mesoporous carbon, which goes by the name of CMK3. And it has conductivity of about 0.25 Siemens per centimeter, and when we stuff it with carbon, the conductivity is effectively the same. So it's like inserting a whole array of conductive posts in the sulfur mass. And the sulfur fills this space. When we melt it inside, it imbibes by capillary action. And we tune the space to accommodate the swelling of the sulfur to form the Li2S. So we actually leave space here for the electrolyte ingress. And also, as I said, ultimately then, this is on solidification, ultimately when the Li2S is formed, it completely fills the space. And this enables the back reaction to occur. In other words, the reaction of Li2S back to elemental sulfur. Because both elemental sulfur and Li2S are extremely good insulators. So that level of contact is necessary in order to actually activate the electrochemical reactions. The other important point is that that array of carbon wires, which are slightly porous, also are somewhat efficient for encapsulating the sulfur. They're not perfectly efficient. So this shows the surface of the electrodes before cycling on the 30th charge for CMK3 sulfur. So this is just sulfur incorporated in the carbon. And you can see on the 30th charge that we do have a sort of a unpleasant looking coating on the surface, which are those insoluble polysulfide, or the soluble polysulfides, which have now reduced to form insoluble sulfides on the surface. And the problem with that is that these are fairly impermeable to lithium-ion diffusion, and therefore they inhibit the reaction. But still, we're doing pretty well compared to some other systems. We have polymer coated these materials with polyethylene glycol, and we find that this effectively completely inhibits this deposition of the glassy sulfides on the surface because they are, for a variety of reasons. One is that they're insulating, and the other is that they act as a hydrophilic gradient. If we divide this by half, which is a figure, which is a typical fudge factor, we would be looking at about 600 to 800 watt-hours for a full cell. And the question then is how to get this capacity cycling for a long period of time. And the other question is how to get cheap carbons to do this. So we've made porous carbon replicas from a colloidal silica. This is just Ludox, nothing fancy, size-controlled Ludox. And these have pore dimensions in the vicinity of about 12 nanometers with a suitably high pore volume and surface area, such that we can now, higher than that of CMK3, so that we can now get 85% sulfur into these materials. And this just shows the sulfur-filled material. Now, we don't actually go to that fill ratio because it doesn't allow us the space for access, but we can get pretty close to that. And what we learned when we did this is that we had quite a problem with polysulfide diffusion, because now we have these 12 nanometer pores and a lot of the sulfur on the outside was escaping. So we borrowed a concept from the drug delivery folks, the pharmaceutical people, who use this material, SBA15, which coincidentally is the silica that we actually used to cast the carbon in the previous studies I mentioned. So these are mesoporous silicas that have pore dimensions that are somewhat along the same dimensions as the polysulfide anions. So we incorporate these to the tune of 5 through 10 weight % in our carbon matrix. And on discharge, to the point where we have a lot of polysulfides, the maximum polysulfide concentration, these incorporate, they're absorbed into these little silica particles. But because this silica is insulating, they don't become reduced, they just simply diffuse out, such that at full discharge, we now have the lithium sulfide, or Li2S2, incorporated in the carbon matrix. So they sort of act as a little reservoir to contain the polysulfides just when we need them, but they are then controlled, they are released in a controlled fashion on full reduction. So the concept then is shown here. If we assume a desorption process, we can calculate on the back of the envelope that about 20 to 30% of them can be contained. And if we assume an absorption process, up to 96% can actually be contained. So this paper has actually come out by now. So the system actually, the concept works. Proof of it is given from careful physical analysis. I'll show you the electrochemistry in a minute. What we did to prove this was we carried out SCM and EDAX measurements of the materials, either at this point, which is the maximum polysulfide concentration, or at this point at full discharge. So at this point, the results shown here, where we analyze one of these SBA15 particles, we see that we have a high sulfur concentration, and we reference to phosphorus because our electrolyte is LiPF6, and it's everywhere, so it's kind of a normalizing factor. So at this point, we have a sulfur to phosphorus ratio of 3.4, whereas at the depth of discharge, at full discharge, it is only 0.2. This just shows the EDAX data. And we are analyzing, again, an SBA15 particle. And we didn't do this, obviously, for one particle. We did them for 100 particles and averaged. And what we learn is that 94% of the sulfur that's absorbed at this point is actually released on full discharge. And the other thing you'll notice here is that there's no glassy sulfide particles whatsoever, even on 40 cycles. So then, to summarize the sulfur part, we've taken, this is data that shows the sulfur in the electrolyte. This is careful chemical analysis of the sulfur concentration. And if you just mix up carbon and sulfur within 30 cycles, you have almost 90% dissolved in solution. The CMK3 manages to hold on to most of its polysulfides for a reasonable amount of cycles. So we were getting about 40% dissolution, but if we modified with the polyethylene glycol, we're down to just above 20%. If we go to a larger pore system, we now have a fair amount of dissolution, whereas if we incorporate these polysulfide reservoirs, we again diminish that polysulfide in solution down to about 20%. So as we've gone from a system where we have lower discharge rates and sort of unacceptable dissolution now to fast discharge rates at about a C rate with very little, 20% dissolution. So this shows the most recent data that we've had, which does not incorporate SBA15, but it's the same sort of principle, just a different porous material. And so we're able to sustain about 850 milliamp hours per gram over 100 cycles, and that accounts for about 77% retention over that value. So we've also been looking at bimodal systems, and that's reported in this energy and environmental science paper that I don't have time to describe. So this is data as a C rate. And the difference between the red and the blue are just different porous materials. And so it's kind of proof of a concept, and this is without the additive in black. So you can see the effect fairly clearly. Okay, in the remaining roughly 4 minutes of my talk, I will tell you about the problems of lithium-air. And so I want to say at the outset that although we are studying this, we are very cognizant of the problems with this system, and I certainly do not intend to overhype this by any stretch. In fact, what I'll probably do is show you all of the problems more so than the benefits, but there's a lot of exciting stuff to be done. So just like in the sulfur case, you need a porous carbon, as I said in this case, to host the Li2O2, which is the reduction product. This has to allow all of the reactants to the active catalyst sites. Catalyst, you say, what's that for? Well, it turns out that oxygen, unlike the sulfur system, which cheerfully reduces and oxidizes, oxygen needs a catalyst, both for oxygen reduction and oxygen evolution. And especially for oxygen evolution, this is an issue. So the porous carbon system has to host the products. It has to maintain electronic conductivity. It is the worst aspect of the fuel cell because you need a triple phase boundary, and the carbon surface area is particularly important. And this has been studied by a host of people over the last couple of years. And what we have learned is that, as I said, there are many problems. So the first is the electrolyte problem. This superoxide species, just like it is in your own bodies where it is, causes aging, in this case reacts quite vigorously with the electrolyte if it's an alkyl carbonate and produces this whole host of materials which then engage amazingly in oxidation. But this is not a lithium-air cell, and it's rather difficult to get these materials to actually oxidize in the cycle. And this was first shown by, at least in the literature, by Doron Orbach in 2000. Mizuno really clearly showed this electrolyte decomposition. Peter Bruce has elucidated how it decomposes, and this group at IBM has determined what the stable solvents are. We have been looking at some of the salts, and we've discovered, as I said, that this tears up almost anything. So even things like LiBob and LiBF4 are chewed up by the peroxide, in this case, for example, to form lithium oxalate. So we have a big problem. The first intermediate is a real issue. So we don't use alkyl carbonates or LiBob or LiBF4. We've been rather slow to publish because we've been trying to get things, as my colleague Yang Xiaohorn said, it's good to get the systems worked out so that no one has to then publish showing how you were wrong. So we're trying to get there before other people show we're wrong. So the IBM group has discovered, or has claimed, that these are stable electrolytes. We have learned that these seem to be reasonably stable. So we're now looking at efforts of catalysts and trying to understand that process better and the role of surface defects. I won't have a lot of time to tell you about this, but I'll just show you some nice pictures. So this is an uncatalyzed system, and this is just carefully designed carbon. That's all there is to it. So you see a nice flat discharge potential exactly where it's supposed to be, no slopes that indicate all kinds of electrolyte messes. This is characteristic of a two-phase reaction, as one would hope. Switch pointers here. And is characteristic of peroxide formation, and we see this in the XRD. It's quite abundant. And a little hard to see here from this number, but this gets to about 7,900 milliamp hours per gram per carbon because it's a nicely defined carbon. And you can also see that the peroxide has nucleated to form these interesting little toroidal aggregates. So this is at 2,500 milliamp hours per gram along the curve, and it's a little hard to see here, but those are shown here. These are sort of pre-toroids shown by these little yellow dotted lines, and you can also see real toroids that are starting to form with these white circles. And this is characteristic of peroxide formation. And the important thing here is that it's not filling the pore space the way we think. It's actually growing right out of the surface of the carbon. And this is further along the curve where you can see quite a field of these toroidal aggregates, again, pulling or literally coming out of the carbon surface. And these don't really grow in size. They start off at about 500 nanometers, and even partway through, they're still only at about 700 nanometers. So it's the number that is increasing as opposed to the actual growth of the particles. And you can see these form, as I said, these interesting toroids, and these are actually agglomerates of tiny crystallites that are about 15 nanometers in size based on shear analysis of the diffraction patterns. So it's particularly interesting to consider how these form because there must be some sort of dissolution and precipitation that allows these to aggregate in this form, and I'll let that open for the question period. At the very end of discharge, again, same thing, more toroids, no particular changes. And the problem is that carbon does not engage in oxygen evolution reactions. You have to take it to 4.5 volts. We cycle between up to 4.3 because we don't want our electrolyte to undergo decomposition. So the reversible capacity drops like a rock for a carbon type system. And so there's a real need for a bifunctional catalyst to decrease this potential on overcharge. It's not so much for this reaction, but it's for this reaction where you really need to minimize or bring down that potential in order to create reversible systems. Now, a few of these have been mentioned in the literature. Alpha MnO2 reported by Bruce, the platinum gold particles reported by Yang Xiaohorn's group. Unfortunately, all of these studies were done in what we call BPC, which is before propylene carbonate, or before propylene carbonate was discovered as having problems. And so they were carried out in a propylene carbonate electrolyte where the oxygen decomposes, the superoxide decomposes a solvent. So the reversibility in these systems is not Li2O2 being charged, it's all those nasty products. So we still don't really know a lot about OER. That's kind of the bottom line today. We have looked at a new catalyst. It's a metal oxide. We've made it porous and nanocrystalline. It's based on a pyrochlore structure. This sheet data shows, this is our favorite electrolyte right now, and this just shows the data for alpha MnO2 either in PC or in TEG-DME. So the take-home message here is that just by changing the solvent, you can increase the capacity even for a poorly functioning system. And it's poorly functioning because, as you can see, although it oxidizes those nasty decomposition products in PC, it really doesn't do it very well in TEG-DME at all. You have to go to high potentials to get that peroxide to oxidize. So our system, as I said, we have a mesoporous version and a nanocrystalline version. This is the second cycle of the cell where the carbon has already kind of died off a bit. So this just shows the pure carbon material. This shows alpha MnO2 in the second cycle, very high potential for oxygen evolution. And this shows the catalyst in a nanocrystalline form, and the catalyst in its mesoporous form. So we're able to get to fairly high capacities in these systems, approaching 10,000 milliamp hours per gram. And we've lowered the charge potential to 3.85 volts. And we know we form peroxide because the XRD shows that clearly. And the most hopeful side of this is that we can cycle the cell. Now, this is only 4 cycles, and I appreciate that this is only a tiny step, but compared to alpha MnO2 or no catalyst, we are at least able to sustain this, even increase the capacity a little bit on the 3rd cycle to, as I said, reasonable levels. What we've actually done is taken the cell apart and discovered that because these cells go slowly, the rate capabilities for lithium-air are pretty pathetic. We have a totally fuzzy white metallic lithium negative electrode at the end. And so what we've done is we've taken the lithium out and we've put fresh lithium in, and we can keep going for another few cycles. So the problem really is protecting the negative electrode. So when we count up the binder and the catalyst and the carbon, we're looking at about 1090 milliamp hours per gram capacity over those few cycles compared to lithium cobalt oxide. So I'll just remind you that the voltage is higher than lithium-sulfur, so that gives rise to a higher energy density, so we can easily get 2,000 watt-hours per kilogram, but really with poor efficiency because it's still of that overpotential. So if anyone had to ask me where I put my money, it would definitely be lithium-sulfur, but the fact is that there's a lot of intriguing work to be done in lithium-oxygen, I think, as we start to, the understanding really expands. So this is just a summary. I'm sort of not quite on time, but this just shows where we've gone from lead acid all the way through the battery regimes of nickel, cadmium, blah, 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 all the way to lithium ion. So I've told you a little bit about sulfur and oxygen, theoretical capacities that are achievable in full cells. And sometimes people ask, heavens knows why, do you ever think that batteries will approach gasoline? And so the answer is no. They won't. Now, we don't have the problems of the inefficiencies of the internal combustion energy to deal with when we're talking about automotive transport either, so there's advantages. And I guess the other take-home message is that we've gone from bulk intercalation to nano-intercalation to what I call nano-integration, and we're getting more and more complex as the demands become more complex. So for those who say that batteries haven't come a long way in the last 10 or 20 years, well, they're just plain old wrong. So I'd like to thank all of my graduate students who did the work. They're all listed here, and most of them have contributed to this. Couple of new students here. David contributed a lot to the lithium-sulfur work, really did some excellent studies, and he's now at Santa Barbara as a postdoc working with Galen Stuckey. And my postdocs, past and present, and some of my collaborators, and these people for funding, and I thank you for your attention.
We have a full house, even though we went over time a little bit.
I'm sorry about that. I knew that would happen.
It's just so much interest. So I want to formally announce this close, so those of you who have other commitments may leave. But I would like to request 5 more minutes for questions.
I think we actually have 15, so, but or maybe we have, if we have 5, if you say we have 5, we have 5.
I'm okay.
Okay.
I'm trying to give you a break.
Fire away. Yes.
I have actually 2 questions. One is for your lithium-sulfur work, as you mentioned, the functioning of the cell is very dependent on the concentration.
Can you turn on your mic, please? Not working. Oh, it's okay, I can hear you, just no one else can, I think.
Yeah, it's being recorded.
That's good.
All right.
Good.
So with the lithium-sulfur, I want to also comment on the lithium-air work. The lithium-sulfur depends very much, as you pointed out, on the molarity of the sulfur in the electrolyte. So I wonder, when you examined your cells with the nanotubes and so forth, do you actually determine the sulfur molarity of the electrolyte?
Yes, in effect. So those results that I briefly showed on the concentration of sulfur in the electrolyte were taken from large cells where we ran them to certain numbers of cycles, as I showed, and we carefully disassembled the cell at each point, extracted the electrolyte, and sent it off to Galbraith for sulfur analysis. Right. So we're determining the molarity, which is basically the amount of sulfur in the electrolyte, and we're trying to minimize that in our sorts of cells.
I see. So, but then in that case also, is also the sulfur molarity in the cell. So it depends.
That is in the cell.
How much excess, what was the ratio? If you take your cell and you calculate out what the molarity of the sulfur would be, assuming that all the sulfur were in the amount of the electrolyte that you have used, what was the number?
So that's the percentage that I reported. So when we measured that sulfur content, those values that I showed you are the percentage of sulfur that is dissolved. I don't remember the molarity values because probably my graduate student worked them out. But that is what is, I think that's what you're trying to ask, right, or what you're trying to get at, which is what is the fraction that's being dissolved? Is that sort of where you're after?
No.
No.
Because if you have a large excess of electrolyte and you don't
I see what you're trying to ask.
Then you can end up with a low molarity but you're still dissolving the sulfur away from the nanoparticles.
Oh, I see. Oh, yeah. No. Okay. So this is, so I would have to get my calculator out because I don't have those numbers at hand. But these are low electrolyte cells. So we don't have a vast excess
you don't have a large
of electrolytes. So the point here is really there are sort of 9 drops of electrolyte in a small cell. Mm-hmm. So it is possible in these cells to dissolve all of the sulfur, but the point here is that we're retaining 80% of it. And that's really the take-home message. Now your question, I'd have to work out
Okay.
We're certainly operating in a regime where if we could dissolve all of the sulfur, it would happen. I think that's the best answer to the question.
Right. The question also with respect to the lithium-air cell, I don't know if your tests were done with dry oxygen or with...
Our experiments are done with dry oxygen. Oh, yes.
Yeah, right.
That's why one wonders about the viability, yes.
The other question is that you also have to have a solvent that is stable to lithium. And, some of the so-called stable solvents to Li2O, Li2O2 may not be stable with
that's
lithium.
why we are guided by the work of the group at IBM, who are our collaborators, and they assure us that these are suitable solvents. Now, none of these are really stable with respect to superoxide formation, but they're somewhat stable. So they're...
DMSO is not okay with bare lithium.
We have time for another question.
Yeah, I'm sorry, we can talk.
I see what you mean. Yes, no, that is not okay for lithium. That's just okay for the superoxide. So we're using TEG-DME, and other groups at MIT are using DME. So we're using solvents that are at least ostensibly stable, and DME and TEG-DME are fine with metallic lithium.
Here. Take the mic. Everything recorded. Would you mind?
Thanks. Okay. So what is the purpose of introducing the fluorine into the battery? I thought the fluorine is toxic, so we're trying to get rid of it. Your first part, you have a F into like the phosphate and the...
You're talking about the polyanion materials?
Yes.
These?
Yes. So you have the F. Also previously there's a iron phosphate.
So your question is, why are we introducing the fluorine?
Yeah.
The fluorine is strongly bound to the system, and it is not accessible for reactivity. It is as strongly bound as the oxygen. It's part of the metal coordination environment. So it's not a toxic substance such as the electrolyte salt. And the point of introducing is that effectively it alters the structure of the material so we can change the connectivity with that incorporation of the fluorine to make new structures that we couldn't. For example, we want to move on beyond lithium iron phosphate. So if you take a look at the same material, instead of sulfur with a phosphorus, it forms this same taborite structure. So the fluorine is not so much important because it's fluorine, it's because it is a negative charged anion that changes the whole structure and charge distribution in the material. And it also increases the potential by a small amount, but that's kind of incidental.
So, Linda,
Jordy.
I want to ask a question first. So
Jordy,
Linda,
just shout it out.
got it.
Well, I know where the mic is.
No, it's okay.
There it is.
Sorry, so, in your opinion, how much sulfur dissolution can we live with?
How much sulfur is what?
How much sulfur dissolution can we live with and still get the battery to what we wanted it to be?
Well,
Is it zero, or can we live with something?
that's a hard question to answer, and I'll be able to tell you in 2 years from now. I'm guessing. You know, the fact is that we still know, for example, if we take a look at this data, where did it go? You know, we have probably, this is a slightly better mesoporous system, but I would guess that we have retained about 80 to 90% in this system as well. So I think it's not a combination. So, but it seems to, you know, level out. So I don't know, is this acceptable over 100 cycles? Well, not if you want a 5,000 cycle battery. No, it's not. But the fact is that this rate of decay really drops off dramatically as you keep cycling, because now you start to precipitate things on the positive and negative electrodes. So that capacity fade becomes almost self-limiting. After a certain point, it stops, because once those layers build up, they don't build up anymore. So the problem can be addressed by interfaces at the positive and negative electrode. And that's what we are working on now, which is why I would say that I'll tell you in 2 years.
I can answer the question, Joey's question actually. At about between 2 and 3 mole of sulfur, you can get up to many, many cycles. So as the molarity of the sulfur and the electrolyte drops, the cyclability increases, but of course the energy
Yep.
density is there.
But I think what you're not realizing is that we're not working in a catholyte cell. So this little picture that I showed here, this is not our design. We don't have sulfur in solution. We're trying to contain it in the electrode itself. So your questions about molarity are a little hard for me to answer, because we're not putting it in the electrolyte. We're trying to keep it out.
Precisely. If you can stay below about 3 molar sulfur in your electrolyte, however much there is, your cyclability will be much higher.
Well, Jordy's question really relates to how much sulfur can you precipitate on the positive and negative electrodes and still maintain ion conductivity such that the system works. That's really what it comes down to. Because if you can build up only thin layers in the cell, and we don't know what those layers are. That's why I can't really answer the question. That's one of the things we'd like to know. But at this point, for example, in the cell, if we have ultra-thin layers of sulfide, insoluble sulfides in both the negative and positive electrode, and the sulfur that's in the cell has effectively been precipitated and it's just sitting there, then we're good to go. The question is, you know, where are we in that limit? So all I can say is that this is probably about 10 to 20% sulfur. And for a typical cell, that'll probably produce a coating that, as long as it's not too thick, will carry on for a while. If that answers your question?
Yeah.
Yeah.
It was a general question. I just
Yeah.
wanted to get your opinion.
So with that, I would like to thank you.
Okay, thank you for your attention.